All right, so I want to say a few words about equidistribution. And in general, equidistribution is really the general, is the underlying philosophy of analytic number theory. And there are several methods of approaching this problem. So basically, the general setting is the following. Suppose that we have a measure space, X mu is a measure space. Such that, let's say, the total measure is 1 or something. So, so that total measure, let's say, is 1. And what we would like, I suppose, is we say that a sequence of elements x1, x2, etc. in X is equidistributed if for all measurable functions f we have the limit n goes to infinity 1 over n summation f of xj, j going from 1 to capital N, tends to equals the integral over x f d mu. So this is the idea, this is the general, super general notion of equidistribution. So I have some abstract space and we have a bunch of points x1, x2 as I move through towards the sequence. I'm, traversing through the space X. And so some way to measure that these points are distributed evenly somehow, uniformly in the space is by asking whether or not this kind of property exists. So that's a general setting. Now it turns out that in some cases of questions of equidistribution, I give you a sequence and I ask you, is it equidistributed in this space? Sometimes the questions of equidistribution can be changed to questions about zeta functions. Okay, and I will try to outline how that works. And sometimes questions of equidistribution cannot be changed into questions of zeta functions. So I'll try to give you an example of both today. One thing perhaps which will be important for our discussion is so let me recall before I say the exercise. Recall that we proved the following. If A sub n's are non-negative, and okay, if you don't mind, let me not do this. No, well, recall the Tiberium Theorem. Okay, so keep that in mind. I'm not going to state that. So we can axiomatize. Actually, this is a method of Sayre. So I'm following Sayre. We can axiomatize our earlier discussions on the prime number theorem and generalizations. As follows. Let G be a compact group for each prime P let X of P be a conjugacy class in G. So for each prime P, I associate a certain conjugacy class. And then the question I can ask is, G is a compact group, so it's certainly a nice measure space. I can ask, as the prime numbers vary, how are these points, these conjugacy classes, let's say points in this space, distributed. So as P varies, how are the XPs distributed? So this is the general this is kind of like a general question. And maybe I should say a few words first how this whole discussion of equidistribution arose. The classical context was studied by Hermann Weyl. Clearly, if you have this satisfied for a dense family of functions in your space, that suffices to check. It suffices to check this condition for a dense family of functions. So the classical setting, goes back to Hermann Weyl, who studied basically the real line modulo integers. So that's essentially the circle, S1. And the question of equidistribution here, he actually came up with a famous criterion, the Viol criterion. A sequence of points xn is equidistributed in R mod Z. So I have a bunch of points on this thing. If and only if e to the 2 pi I x, e to the 2 pi I m times x sub n, n going up to capital N, each of these sums divided by n tends to 0 for all m, which are integers. M is of course not 0, because if m is 0, this is just 1. M is 0. Okay, so you want this to happen. Now, how does one prove this? So you want to check. So getting back to our definition, for any measurable function, measurable functions are also approximated by these step functions, right? So you can reduce the whole business to piecewise continuous, or step functions. So or continuous functions are dense in these spaces. So you could kind of reduce your thing to continuous functions. So we have to check well, here in our group, our space is R mod Z. So you have to check that this is equal to f of x dx, the usual business. Maybe I should write integral 0 to 1, just so that it's clear to them. So you have to check this. Need to check for all continuous functions, right? Now, the space of trigonometric polynomials is dense in the space of continuous functions. Therefore, it suffices to check it on trigonometric polynomials. And so this should not come as a surprise. Everybody okay with this? So clearly, if this is equidistributed, I just apply this criterion with this function. So one way is obvious. And you just have to go the other way now. The other way comes from the fact that these functions are dense in the space of functions. The trigonometric polynomials are dense in the space of continuous functions. Okay? So that's how you get this. This is called the Viol Criterion. Okay, now, what is interesting is that this is really a special case of a compact group, R mod Z. And so if you were to generalize this situation to a compact group, you would look for continuous functions on this compact group. And the space of continuous functions is, it turns out, the family of characters of irreducible representations of this group are dense in the space of continuous functions. That's what's called the Petter-Viol theorem. So the Petter-Viol theorem tells us it's not Peter, but it's Petter, okay? That's important pronunciation. Tells us that the space of class functions, so these are functions which are constant on the conjugacy classes, the space of class functions is, well, let's say the irreducible characters are dense in the space of class functions. And so the Viol criterion for a compact group translates as, if I have a sequence of points, all I have to do is check. So if this thing is equidistributed in G, if and only if I take an irreducible character chi, and I show that it's equal to 0 for all irreducible characters not equal to the trivial character. Okay, so the Viol criterion for a compact group translates in this fashion. Okay? So Sayre got this very nice idea of kind of formalizing the success story of the prime number theorem, that we were able to prove equidistribution, distribution of prime numbers, primes in arithmetic progressions. We could get all that stuff if we can axiomatize the whole mess by doing the following thing. So for each prime p, I have a certain conjugacy class, and we associate to each irreducible representation rho of G an L function like this. Okay. Now, because the group is compact, all the eigenvalues, firstly, all the irreducible representations are finite dimensional, standard group theory there, and the eigenvalues are all roots of unity, therefore bounded by 1, and therefore this converges absolutely for real part S bigger than 1 for each of these things. So Sayre begins by saying that suppose theorem, suppose for each irreducible rho not equal to 1, LS rho extends to real part S greater than or equal to 1 and does not vanish there. Then by the Tiberium Theorem, essentially, so he doesn't, that's the proof via the Tiberium Theorem. Chi is the trace of rho, by the way, trace of rho. So there's a representation, there's a character attached to the representation. So chi of x sub p, p's, I'm just using p's as primes. 1 over pi of x is the number of primes, goes to 0 as x goes to infinity for all chi not equal to the trivial character. So he proved this. I mean, that's, and you can prove it too because you have all the tools. You just have to check what happens when I take the logarithmic derivative of this object here and see what the terms are, and it turns out that it's this thing, and when you apply the Tiberium theorem, you get this. If it doesn't have any zeros, you get this. And so now this, interestingly enough, maybe I should point out that in the application of the Tiberium theorem, we said that if the Riemann zeta function didn't vanish on the line real part S equals 1, then you got the asymptotic formula. Conversely, if you have the asymptotic formula, that is, if you have the prime number theorem, you can go backwards. I'll leave that as an exercise and show that the Riemann zeta function doesn't vanish on the line real part S equals 1. in general, it goes both ways. So if you have this, you certainly have this if these things don't vanish on the line 1. Conversely, you can go backwards. If you have this, then these things don't vanish on the line 4. So it's a kind of an if and only if. This is, by the way, why many people believe there was no elementary proof of the prime number theorem. Elementary meaning a proof of the prime number theorem which avoids the use of complex analysis. Now there is such a proof, but it comes via sieve theory, which is another game altogether. But the most straightforward approach to the prime number theory and things of this nature is through complex analysis. Yeah. So here's the general theorem. So let's try to think about some applications now that we understand equidistribution. As I emphasize in my problem books, the only way to learn mathematics is by doing things rather than reading things in the abstract, right? So let's have a look at a few applications. So so here are some examples. Let's try work through them. Let theta be an irrational number. Prove that the sequence n theta minus the greatest integer of n theta. So this is my sequence x sub n, okay? X sub n is this thing. N going from 1 to dot 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 is equidistributed in the circle. That means these fractional parts are always between 0 and 1, right? I can think of them as on the line 0 to 1, right? And so trying to show that this equidistribution. No. Okay, so we have several ways of approaching this. We can first start with the Viol criterion. So apply the Viol criterion. Try and see, can I get my hands on, is it equidistributed or not? Now, if it's equidistributed, what do we have to check? We have to check that summation, so we need to check summation e to the 2 pi I m x sub n, n going from 1 to capital N, 1 over capital N, tends to 0 as n tends to infinity for every m integer which is not 0. So have to check this. If that happens, then it's equidistributed by the Viol criterion, right? I said that here. Okay. So let's try and figure this out. So we have to examine these sums. X sub n, right? But x sub n is n theta minus the greatest integer n theta, right? Have to study this sum. But either 2 pi I m times this greatest integer is just 1. So you can drop this. Okay. Now I have a geometric series here. which you can all sum, right? So I factor out either 2 pi I m theta, and then I have 1 plus, whatever, either 2 pi I m theta to the power n minus 1 divided by exactly, right? Provided the denominator is not 0. But can the denominator be 0? Why not? Theta is irrational, exactly. That's why I had to put an irrational number. So you're in trouble if theta is rational, right? At this stage. Let's just worry about this for now. Okay, so now we have this. And what do we have here? We have a number which now, this number doesn't depend on capital N. The denominator doesn't depend on capital N. The numerator does, but it's bounded by 2, right? It's bounded by 2. So this numerator is bounded by 2. This guy is all independent by n. So if I divide by capital N and take the limit as n goes to infinity, it's 0. So it satisfies the Viol criterion. Okay, so this is equal to little o of capital N for any m not 0. And so it satisfies Viol's criterion. Therefore, that sequence of fractional parts is equidistributed in the circle. Right? So we have that. Neat and tidy. Okay. What happens if theta is a rational number? Remember, Viol's criterion says the thing is equidistributed if and only if the Viol condition is satisfied. If and only if. So is there an m for which this condition is not satisfied? Let's say theta is equal to p over q, right? Let's say, right? Choose m equals q, and all of these are now just ones, and the Viol for m equals q, the Viol condition fails, right? So I can say it is not equidistributed. And actually, intuitively, you should be able to see this, because if I have a rational number, p over q, and I'm looking at multiples of that thing, remember, it only depends on the remainder, and the value of the fractional part is actually 1 over q, 2 over q, or q minus 1 over q. These are the only values. So as I move through the thing, it's only taking some fixed values and never kind of moving kind of continuously through. It's a very discrete kind of thing, right? There's these big gaps. So clearly it's not equidistributed. To say the sequence is equidistributed means it kind of fills up the space, as it were, right? So you can see that this is some method. The whole idea, the philosophy behind equidistribution is to try to understand a random sequence or a sequence that you really don't know anything about to get some understanding of how it's moving around. So this gives you now some information. In fact, it gives you a criterion to figure out when a number is rational and when it's not irrational, right? This way. Okay, let me just change the question a bit. So by the way, these things are called fraction. This is the fractional part, right? I mean, so the fractional part of x is by definition x minus the greatest integer. This is the usual. So let me ask you, let P be prime. Is the sequence fractional part of log P as P varies equidistributed? Okay. Okay, so we have our famous Viol criterion. So we have to check, need to check so the number of primes is a pi of n, right? So we only count these. This in this sequence, we have to need to check whether or not this goes to 0 as n goes to infinity for all m not 0. That's what we need to check. If it's equidistributed or not, we have to check this. If for every m this happens, it's equidistributed. If for some m it fails, it's not equidistributed. Okay? Now we run into a problem because I don't know how to do that. Okay? Here it was nice because we had a geometric series. Here now you've got primes all over the place. Doesn't look very good. So this is where Sayre's formalism comes in handy. He's telling you, if I have an assignment of elements for each prime p, I'm associating some element xp, which is either an element in some space or conjugacy class in some compact group. There's a way to set up these L functions and to check for each L function whether this is the case. So now we can do that here. We can try to do that. Our group is R mod Z, and so we have an assignment. The Viol criterion, so if I was to apply Sayre's formalism to G equal to R mod Z, then I can do the following. I can look at the assignment P goes to XP to study the distribution of this sequence by looking at the L functions associated to each irreducible character of this particular group. This group is an abelian group. All characters are given by psi sub m of x is just simply either 2 pi I mx. Now, I'm not going to prove this. That's a theorem from group theory, okay, or representation theory, or whatever you want to call it. So this is a compact group, compact abelian group actually. So all characters are given by this. Therefore, how do I construct an L function? Well, there's no need to take the determinant because it's not a big representation, it's just a character. So L as psi sub m is equal to product over the primes p. Well, the determinant is just 1 by 1. So it's 1 minus psi sub m of x p over p to the s inverse. So these are your L functions that you would have to study in the context of the Sayre formalism. Okay? Now, if you try to put these L functions in this problem, when I asked you whether or not M, whether or not these fractional parts are equidistributed. If you try to do that, these L functions are very unwieldy. Okay, so you have to know when to use an L function and when not to use one. So in this case, you shouldn't use it. You should go directly to the Viol criterion and just check. What is Sayre doing after all? He's getting you to the Viol criterion through the agency of an L function. If you could have gotten to the Viol criterion without going through an L function, which you did in this case, just do so. But sometimes you get stuck, and therefore you may have to do this. So let's look at our sequence. Our sequence is log p. P goes to log p. So our L function in this case is just simply p 1 minus e to the 2 pi I m log p over p to the s inverse. Okay. Now either log p is just p, right? So this looks like a familiar object, doesn't it? It looks like the Riemann zeta function at 2 pi I log p, 2 pi I m, sorry. It's over, right? This is the Riemann zeta function at s minus 2 pi I m. So all the L functions that Sayre is asking you to analytically continue, well, you've continued them. They're all here. However, it should not vanish. It should not, except for a pole. But I should have said, well, the pole is for the trivial character. So this is not analytic. This has got a pole at s equals 1 plus 2 pi I m. So this has a pole. I'm running out of space. This has a pole at s equals 1 plus 2 pi I m. Exactly. Now remember, I told you this theorem that Sayre has proved is actually an if and only if. That is, if you have this, then you have this. If you have this asymptotic s, then you have the non-vanishing. There are no poles. I've just got a pole there. So if it was, so you start out by saying if it was equidistributed, you apply this theorem in the opposite direction. If it's equidistributed, then the associated L function should not have a pole, but it does. Therefore, the fractional parts of log p are not equidistributed, which is, you could never have guessed it. Could have never guessed it. You need the zeta function to say that. And you need this kind of mechanics. Okay? I mean, there are more things that you could say. Perhaps tomorrow I can say more things about L functions and equidistribution in general. Talk a little bit about Chebotarev density theorem and so on and so forth. But now let me kind of show you another example where this mechanism of L functions is probably the dumb way of doing things. I mean, sometimes it's a good way. Sometimes it's a dumb way of doing it. You have to figure out when it's the good way and when it's not. There's not just one thing that moves, right? So let me ask a simple, very simple question. Let's study a few things and ask something about equidistribution. I mean, the whole notion of equidistribution is the underlying philosophy of analytic number theory. Tries to understand how things are distributed. And so this is the. So let's look at what are called Gauss sums. Sometimes these questions of equidistribution can be very difficult, and I want to illustrate such a occasion by asking a very simple question. So let's see. Let's consider Z mod PZ. P is a prime. Okay, so let us consider the ring Z mod PZ. On one hand, it's an additive group. On the other hand, it's got the multiplicative full-prime residue class, right? And you know that the characters, as I mentioned there, kind of, it's either 2 pi I mx over p. So these are your characters of the additive group. So these are the characters of the additive group. And now when we look at the multiplicative group, well, we already have met the Dirichlet characters. Dirichlet characters. These are the characters of the multiplicative group, right? And the Gauss sum tau sub A chi is equal to if you don't mind, I just want to give this a name, psi of mx. This thing. Okay. So this thing can be written using my psi notation. Now these Gauss sums are very useful in number theory. Maybe you've already met them, but if you've not, here they are. Okay. The Gauss sum is supposed to be thought of as some sort of finite analog of the gamma function that you may have studied in complex analysis. The gamma function. The gamma function is often defined in this fashion for real part as positive, and it's analytically continued using the functional equation gamma s plus 1 is s gamma of s, right? So what's going on here is, in some sense, you have you're looking at the ring R. Well, it's a field, but anyway, I'll like to call it a ring for a moment. Okay, so you're looking at the ring or the additive group, and characters of the additive group are given by t goes to either t. Those are your characters. The multiplicative group, which is the non-zero elements, breaks up into two connected components, the positive and the negative. And so we're integrating over some one connected component, and these are your multiplicative characters. So this is the multiplicative character. This is an additive character. And so here I have a similar phenomenon. I have a multiplicative character, and I have an additive character. So the Gauss sum is some sort of finite field version of the gamma function. Now this kind of poetic analogy actually is very useful in proving lots of theorems, because the gamma function has been studied for about 4 centuries now. Lots of theorems have been proved. But the Gauss sums are relatively speaking, new, maybe 2 centuries old or something like that. Therefore, we can try to understand these Gauss sums. They turn up all over the place. And we'll try to look at them now and see what can be said about them. Most of you have seen these Gauss sums before, somewhere along the way? Or meeting them for the first time? First time? Okay. Well, they'll be very useful in life for sure. And you know, sometimes if you want to do research, it isn't such a bad idea to just go into the library and take out a calculus book where there are identities with the gamma function and just ask yourself, what's the corresponding version for Gauss sums? Most likely you'll get a paper out of it. If it's, but that's not a bad idea. You probably should do that. It's a good way to do research. So this, what is called research by analogy. So we made an analogy. The Gauss sum is analogous to the gamma function. Therefore, theorems of the gamma function should have a corresponding theorem here. A theorem here should have a corresponding theorem there. So you can kind of go back into 2 different worlds and kind of get interesting results. So what can we say about the Gauss sum? Let's see. For one thing, if A and P are relatively prime, well, firstly, if A is 0, this is 1, right? And we already saw the character sum chi of x is going to be 0 or 1 depending on when it's trivial or not. So we know about that. So let me just say that here. So if A is 0, tau sub 0 of chi, well, it's either p minus 1 if chi is trivial, oops, and it's 0 otherwise, right? So this is pretty easy. Figure that out. If A and P are relatively prime, well, we could do the following. We notice that tau sub A of chi is equal to x in z mod pz, chi of x, 2 pi I a x over p. What I'm going to do is I'm going to set ax over p to be b. Okay? If I do that, this is mod p. A is not 0, A is relatively prime. So that means x has to be A inverse b, right? Mod p. Because A is not 0. So I can change variables and change ax as x runs through all these residue classes, so does ax. Kind of an automorphism. So you have chi, x is now A inverse b, either 2 pi I b over p. And as x is running, so is b, so b mod p. Let me just put something like that. Okay, instead of now chi is a multiplicative homomorphism, so chi of A inverse is chi bar of A. So this is just simply chi of B, either 2 pi I b over p. Fair enough? In other words, tau sub A of chi is the same as chi bar of A, tau sub 1 of chi. So the first thing you'd like to do when you're confronted with a certain sum, how big is this silly thing? So let's try and figure that out. Now we will do it cleverly, of course. You could do stupidly. Stupidly, I guess everything is bounded by 1, therefore it's at most p. So stupidly, maybe p minus 1 because there's a 0, right? So you have something like this. So can we do better? Well, consider summation tau sub a chi squared, where I sum over all the a's. Let's make, let's see, should I do a? Yeah, a not 0. Okay, let's just sum over all the a's not 0. Well, because this is chi bar of a squared, so this we know that each one of these things is modulus of chi of a squared. Mod so this is on one hand mod of tau sub 1 of chi squared summation chi bar of a squared, right? A not 0. But each of these is 1. So I end up getting p minus 1. So on one hand I get p minus 1 times tau 1 of chi squared, right? Fair enough? Okay, on the other hand, so I calculated it on one way. On the other hand, let's plug in this formula in here and expand. You have no other choice. On the other hand, so what am I going to do? I'm going to put x and y, chi of x, chi bar of y, either 2 pi I a x minus y over p. Fair enough? And we interchange summation when you see two sums, that's about the only thing you can do. Okay, interchange summation. Now if x equals, oops, I forgot a bar here. If x equals y, the inside sum is p minus 1. X equals y, mod y squared, and I end up getting p minus 1 squared, right? If x equals y. If x is not equal to y, if x is not equal to y, what is that sum? Well, 2 pi I x minus y over p is a root of unity, and I'm summing basically, so let's say zeta is either 2 pi I x minus y over p, let's say that. Then the sum inside sum equals zeta plus zeta squared plus zeta to the power p minus, somebody said it, p minus 1? Yeah. Good. Which looks like zeta, and looks like the same calculation as before, zeta to the power p minus 1 minus 1 over zeta minus 1, right? Zeta is not 1. This is not 1 this time. We're okay? Pardon me? Is there p minus, let's see, I factor out zeta, and I get 1 plus zeta squared up to zeta p minus 2, so it's 1 more than that, yeah? And then you see that the top is zeta to the p, which is 1, minus zeta over zeta minus 1, which is minus 1. So this answer is minus 1 in this case. Okay? Everybody okay with that? Sure, you can do that at home. Yeah. Okay. So now what we could do is we could let x equal y and then throw the thing back in, right? So this can be written as minus summation chi of x, chi of y, plus x equals y, chi of x, oops, chi of y. Is that fair enough? So all I've done is I have removed the condition x not equal to y by doing this silly trick of putting everybody in and removing that thing out. Okay? The advantage is if chi is not a trivial character, so chi is not a, so we're going to make sure chi is not trivial. Okay? Chi is not the trivial character, then this guy is 0. Right? And this guy is 1. And how many elements do I have? P minus 1. So this is equal to P minus 1 squared plus P minus 1. So on one hand, the calculation gave P minus 1 times this. On the other hand, the calculation gave P minus 1 squared plus P minus 1, which looks to me like P times P minus 1. Therefore, I can cancel the P minus 1 and deduce that this guy has absolute value root P. Okay? Tau 1 of chi is a complex number with absolute value root P. Tau sub A of chi is nothing but the same guy twisted by this character, so it's still absolute value root P. So here are these family of numbers, tau sub 1 of chi. As I range through chi as characters, I can try to study them. They're numbers with absolute value root P. So the first question that you ask is, I've got a whole bunch of them, one for each character chi. I've got P minus 1 characters. And so I may ask, what can I say about? Are they all, like, maybe they're all equal to root P, right? So we've proved theorem. Tau 1 of chi is root P. So when chi is not the trivial character. Okay? So that tells me something about these numbers. But now the next question is, they're sitting on a circle of radius root P. So the question is, how are they sitting there? And now the question of equidistribution comes into the picture, right? So is the sequence which is now a complex number of absolute value 1 equidistributed in 0, 1. I mean, is it equidistributed in that? Sorry, on the unit circle, on S1. On the circle. Okay, I'm running out of time, but maybe let me just say what the kind of how, I mean, this looks like a very innocent question. Could have been asked by Gauss, but I don't think he did. Because remember, this whole business of equidistribution starts later with Hermann Weyl. So one could ask this question, but I would say that Gauss may have very well had difficulty even if he asked the question, it would be one of these questions that you couldn't have answered at that time. Okay, so let's see why. It's very simple. So tau out of x, tau out of chi rather, is chi of x e to the 2 pi I x over p, right? This is what x mod p. That's the Gauss sum, right? And if I'm interested in, so let's look at this guy and write it as e to the phi p for some angle phi p. So I'd like to know whether this is equidistributed or not. And Hermann Weyl tells us that you have to consider, to check equidistribution, one needs to study summation e to the 2 pi I m phi sub p, p less than x. For each m, we need to study this. Okay? And we need to show, sorry, not p less than x. I'm ranging over characters, right? So phi p of chi, I should have called this phi p of chi. So I'm ranging over the characters. So for each character chi, and then how many characters do I have? P minus 1 characters, right? I need to check that this goes to 0 as p goes to infinity for all m not 0. This is what we need to check. So why not leave it to you to mull over this question? It's not easy. Mull over this question. Tomorrow I'll tell you how it's done. I can't tell it. I can't answer the question because you need some sophisticated machinery. But anyway, it's not a bad idea to think about this stuff and discuss it in that context tomorrow. And tomorrow also I will discuss more general theory of L functions and zeta functions and how those things pertain to questions of equidistribution in general, and at least lead you up to some of the modern questions in analytic number theory. Okay. Do you have a question? Okay.